Hello, chemists! This is Miss Placino, and you are watching lesson 2.2 on the Bohr model of the atom. Today's lesson, we're going to talk about really how the Bohr model of the atom came to be. If you think back to lesson 2.1, we spent some time talking about how J.J. Thomson's model of the atom, the plum pudding model, replaced the billiard ball model, then how Ernest Rutherford's model of the atom, the nuclear model, how and why it replaced the plum pudding model of the atom, but we never really talked about how the Bohr model came to supplant the nuclear model of the atom. So we will talk about that today. Some goals for the lesson. Make sure that you can explain what the atom looks like according to the Bohr model. We're going to be able to draw the Bohr model for any main block element. Usually it's just elements 1 through 20, but we're going to do anything that's in either columns or groups 1, 2, 13 through 18 in the periodic table. And really understand ground and excited states and how energy plays a role in transitioning between them. All right, let's get into today's lesson. Okay, so we know that Ernest Rutherford, through the gold foil experiment, discovered the nucleus. J.J. Thomson discovered the electrons, and we know that most of the atom is empty space. However, how did we make the jump from positively charged nucleus, electrons just anywhere, to something that looks really organized like the Bohr model of the atom, where we still have that positively charged nucleus at the center, but now there are rules about where the electrons can be? So really, how did we disprove the nuclear model of the atom? And the answer comes down to watching how light interacts with matter. So scientists at the time used these devices called gas discharge tubes, and we'll be using them in the lab. Basically, inside this little glass tube is a gas, whether it's hydrogen gas, neon gas, helium gas, any element that's in the gas phase is really easy to work with. You can also get elements that are typically not in the gas phase to become gases in the gas discharge tube, like sodium, for example. So we're going to plug it into an electricity source, and we're going to pass electricity through that gas. And as that happens, the electrons within the gas are going to gain some energy, move farther away from the nucleus, then lose that energy, come back closer to the nucleus, and release light. If you felt like I moved through that a little too quickly, don't worry, we'll be revisiting it in just a couple of slides. So again, we've got our tube containing excited H2 gas. That just means that we've passed an electrical current through it. It's going to give off light, much in the way light's being given off here. We're going to take that light, we're going to pass it basically through a narrow slit, through a prism, which will serve to split the light into its different components. So again, electrons will absorb energy, move away from the nucleus, and as the electrons come back closer to the nucleus, they will release that energy as some form of light. We'll detect it, and that's going to give us some insight into the structure of the atom. So assuming the nuclear model is accurate, every element, regardless of the identity of that element, would give the same spectrum. We'd see the continuous spectrum, every single color of the rainbow. Basically, if an electron is able to move anywhere between any 2 points, if it moves really far, say from the outer edge almost all the way back to the nucleus, it would have lost a lot of energy. So we'd see a purple color. If it barely moved at all, we'd see something closer to the red, but every option in between. You can think about this as a ramp. This is a good analogy, where energy is continuous. I'm sure you've been on a ramp before, and you know from personal experience, you can stand anywhere on the ramp. Well, maybe up here is kind of tough, but if you really needed to, you could probably stand on the very edge or the very top as well. So, again, just to summarize, since electrons can move between any 2 locations, a continuous spectrum, all the colors of the rainbow, would be observed. So this is what scientists were expecting to see. However, this is not what was observed. Scientists got this. This is called an emission spectrum. And this in particular is the emission spectrum for hydrogen gas. It didn't matter how many times they tested hydrogen gas, how much electricity they passed through that gas, they still got these same 4 just strips of light, wavelength of violet, blue, green, and red. Scientists concluded there must be some rules about where the electrons can exist. In the previous lesson, we talked about energy being quantized, and I said, don't worry, we'll kind of revisit it. Well, guess what? It's time to revisit it. When energy is quantized, it's not like a ramp. It's more like a staircase. I know you have plenty of experience with stairs. I can stand on the second stair. I can stand on the third stair. Is there any way to stand on the stair 2.8? No, of course not. It doesn't even really exist. It is impossible to occupy the height or the step that would be equivalent to 2.8. You have to be on the second or the third step. Don't believe me? Try to stop on the 2.8 step next time you're on a staircase. It's not going to go too well for you. Hopefully you just drop down to the second step and take a header down all of them. This is what we mean by energy is quantized. They're like discrete levels of energy that are allowed. So again, we see an emission spectrum, and as a result, we've got to change our model of the atom. There's no way the nuclear model of the atom would produce an emission spectrum. So Niels Bohr proposes the Bohr model of the atom, where we've got these rings or orbits or energy levels or whatever you'd like to call them. Shells comes up a lot too, that are specific distances from the nucleus. Okay. So let's talk a little bit more about how those emission spectrum are produced. So what we have here is a Bohr model of the atom. We'll work with something simple like hydrogen, so we just have one electron to deal with. We still have our positively charged nucleus at the center, and then we've got 3 different energy levels for the electron to exist at. Right now, the electron is as close to the nucleus as it can possibly be. We call this the ground state, and under normal circumstances, atoms tend to exist in the ground state, or the electrons of atoms tend to exist in the ground state. 2 different ways of saying the same thing. It is possible for me to excite these electrons. I can provide energy to that electron, usually by either heating it up or passing an electrical current through it. So go ahead, draw a squiggly line that's supposed to represent light being absorbed by the electron. That's going to cause the electron to move further away from the nucleus. Depending on how much energy it absorbs, it might bump up just 1, maybe 2, maybe so many energy levels it doesn't even belong to the atom anymore. But we'll assume it's just 1. In this middle Bohr model, the atom is in the excited state. The electron is not as close to the nucleus as it could be. It's excited. The electron can't maintain that excited state forever. Think about you in an excited state. If you try to pull an all-nighter and you stay up by drinking Red Bull or Monster or coffee, eventually you're going to crash. There's no way to maintain that state unless you continuously put Red Bull into your body. There's no way for the electron to maintain the excited state without continuous amounts of energy. So, assuming it doesn't have continuous amounts of energy, it's going to emit energy in the form of light, and it's going to drop back down to a lower energy level. And if it drops all the way back down to the lowest energy level, as close to the nucleus as it can be, we've said that it's entered the ground state again. So just to kind of rehash that ground state, electrons are as close to the nucleus as possible. Energy gets absorbed by the electron. They move farther away. We call that an excited state. Eventually, the electron will give up that energy. It will emit it in the form of light, and it will return to a lower energy level. And that's how we get the emission spectrum. So we're going to do a little bit of practice with ground states and excited states. But before we do that, I just want to lay out some ground rules about how many electrons can exist in each of these energy levels. So with our ground state configuration, the max number of electrons that each orbit or energy level or shell, whatever term you'd like to use, can hold. The first energy level can only hold 2 electrons. It's very small, it's close to the nucleus, there's not a lot of space to pack them in. As you move a little bit further away from the nucleus, you can squeeze in more electrons. So the second energy level holds a total of 8 electrons. The third, even farther away, even bigger, can hold 18 electrons. Our fourth energy level can hold 32 electrons. And don't worry, you're not going to have to draw all of those electrons. You might be wondering, like, where exactly did these numbers come from? It's a little bit too much to get into in this lesson, but we will revisit that concept in future lessons. As far as the ground state is concerned, there's only one ground state configuration for each element, and you can find it by looking on the periodic table. In fact, let's go ahead and do that now. Okay, so here we are in the periodic table, and the periodic table is just chock full of information that is really, really useful. If we just kind of look at the key, there's a ton of different numbers to contend with in each element box. The electron configuration is the string of numbers underneath the atomic number. Now, those string of numbers will always add up to the atomic number, because in a neutral atom we should have the same number of protons as we do electrons. And this string of numbers is just telling us how many electrons are in each energy level. So in something like carbon, we've got 2 electrons in the first energy level. It's now full. The remaining 4 are going to be in the second energy level. And really, for each element, it's spelled out pretty clearly how many electrons are present and how they are arranged according to the Bohr model of the atom. Let's do a practice problem or two together. I want to take a look at, let's look at magnesium, since it's a little bit more involved than lithium. So I'm being asked to draw the ground state configuration. I'd want to go back and look at my periodic table, find magnesium. Here's magnesium right here. It's got the electron configuration 282 in the ground state. That is the only ground state for magnesium. So I'm going to go ahead and start to fill in my energy levels. We can just use dots to represent the electrons. There's 2. They tend to come in pairs. 8. Another 2. I am not particularly concerned with how you arrange them. As far as do you make them pretty equidistant from one another, how you set it up. As long as you've got the correct number of electrons in each energy level, I'll give you some flexibility. So our ground state configuration is just 2, 8, 2. And again, that is the only possible ground state for magnesium. If I want to make an excited state for that element, what do I need to do? I've got to take at least 1 electron and I have to promote it to a higher energy level. There are kind of like almost an infinite number of possible excited states. So let's say I'll keep my 2 in the first energy level. I'm going to put 7. 1, 2, 3, 4, 5, 6, 7 in the second energy level. So that's given me 9. I need 12 altogether. So maybe I've got 3 in the third energy level. I know that's an excited state configuration because not all of the the electrons are as close to the nucleus as possible. One of them has been promoted into the third energy level. Another really easy way to do it is to take 1 electron from the outermost energy level and bump it 1 further. So something like a 2-8-1-1. That's an excited state. Plenty of different excited states to come up with. Only real rule you have to, 2 rules you need to keep track of. First, make sure that you still have the correct number of electrons. In the case of magnesium, we need 12. Rule number 2, make sure you don't break any of the maximum number of electrons that each energy level can hold. For example, if I did something like 1, 9, 2, that isn't going to work. Why not? Because I've got 9 electrons in the second energy level, and it maxes out at a total of 8. Get all that stuff out of the way. Just for a little bit of review, we can look at number of protons and number of neutrons. Magnesium has an atomic mass pretty darn close to 24. It's got 12 protons in its nucleus based on the atomic number. 24 minus 12 is 12. Showing off the math skills. So I've got 12 of each. That's really all there is to it. There are plenty of other practice problems for you to play around with. Keep in mind there's only one correct ground state for each element. It is on the periodic table. And then you have a multitude of possible excited states. Just make sure that you are having the same number of electrons that you do in the ground state, and that you have not put too many electrons in an energy level. All right, that wraps it up for today. Thank you for tuning in, and I hope you found this helpful.